Welcome to this short video, which is a guided tour through the use of the Wale 2003 spreadsheet. All data and formulas used in these interactive spreadsheets is based upon information contained in the 6th edition of Formwork for Concrete SP4 by M.K. Hurd. Using these spreadsheets can assist you in understanding wall design in detail in order to provide a solid background for exploring and studying today's more complex formwork systems. The spreadsheets are organized to closely mirror the design process and detailed examples as presented in SP4. Once you open up the Excel spreadsheet as we have done here, you will notice that there are worksheet tabs at the bottom of the screen. For example, Introduction, Pressure, Plywood, etc. Click on the Introduction tab at the bottom of the screen. You will notice a description on the Introduction worksheet about the color scheme that is used in these spreadsheets. Numbers that appear in blue are input by the user, while numbers that appear in red are the spreadsheet's calculations based upon the formulas. The label tabs at the bottom of the screen down here represent the sequential steps associated with designing a simple timber-based wall form system. The tab worksheets begin by calculating the initial design lateral pressure here, and end by determining the spacing of the lateral braces here. If we click on the Pressure tab, you can see that this worksheet is for determining the initial design lateral pressure. The user inputs all values in blue: the weight of the concrete, the temperature of the concrete, the rate of placement, and the height of the wall. With this information, the spreadsheet will calculate the design pressure, assuming the concrete meets standard conditions, and utilizing the lateral pressure of concrete equations as per Guide to Formwork for Concrete, ACI 347R-94. These same equations and associated discussions on their appropriate usage can also be found in Chapter 5 of SP4. In this example, based on the given input here in blue, the design pressure is calculated to be 600 psf. The Plywood tab down here is where the user can select the thickness of the plywood, the orientation of the face grain, either perpendicular or parallel to span, and the usage factor, either single use or multiple use. Based on the wall form example in SP4, the user selects 3/4 inch Plyform BB Class 1 sheathing, assuming single use and face grain parallel to span. The spreadsheet then determines the controlling maximum stud spacing based on bending, deflection, rolling, and shear calculations. You can see this more in depth by clicking on the tab labeled Calculation Summary down here at the bottom. If we return to the Plywood tab, we can see that in this example the controlling stud spacing based upon bending is 12.61 inches. Assuming an 8-foot module, standard sheet of plywood, the user should use a practical stud spacing of 12 inches center to center. The Stud Wale tab is a worksheet used for selecting stud properties and calculating the controlling wale spacing. In this example, the user selects Douglas fir larch number 2, S4S, 2x4s, assuming single use, no splits, and a moisture content less than or equal to 19%. The spreadsheet again calculates the maximum wale spacing for this type of stud based upon bending, deflection, and horizontal shear. Again, if you click on the Calculation Summary tab at the bottom here, and then you take your mouse and drag and scroll down the page a bit, you'll see this area called wale spacing using stud size. This will show you more details about this calculation. Upon returning to the Stud Wale tab, We can see that in this particular case, the spreadsheet returns a maximum wale spacing of 31.67 inches, with the allowable bending stress begin controlling. Based on the wall height of 14 feet that was input previously in the pressure tab down here, we can see that the stud wale worksheet shows us that the user should select a practical wale spacing of 30 inches center to center. The wale tie tab is the worksheet for selecting the wale properties and calculating the controlling tie spacing. In this example, the wale size is unknown. However, the user can input the other known properties of the wale system, namely that they are Douglas fir large number 2, S4S, double wales, assuming single use, no splits, and a moisture content less than or equal to 19%. Next, the user inputs the tie capacity in pounds of a safe working load, down here. In this case, 4,500 pounds. The spreadsheet then takes the safe working load and divides it by the uniform load on the wales, that is 1,500 pounds per foot, based on the selected practical wale spacing of 30 inches that was established in the stud wale tab, right here. The result of this calculation, that is 4,500 pounds divided by 1,500 pounds per foot equals 3 feet, sets the maximum tie spacing based upon the tie capacity only at 36 inches, or 3 feet. Next, the spreadsheet assumes bending will again control and applies the allowable bending stress formula. That's equation 618 in SP4. To solve for the minimum section modulus S required. The spreadsheet then sorts the dimensional lumber table records, table 4-1D in SP4, by ascending S values. The spreadsheet is programmed to perform a vertical lookup and return the piece of dimensional lumber that has the next higher value of S as compared with the calculated minimum required S. The program will suggest a wale size based upon tie capacity only. In this particular case, a 3x4. The user can then input the wale size into the cell entitled Enter Wale Size for calculating tie spacing with wale capacity only. The program again runs the calculations for the maximum tie spacing for this type of wale based on bending, deflection, and horizontal shear. Again, if you click on the Calculation Summary tab at the bottom of the screen here, and you scroll down a bit on the page, you can see more details in the area labeled tie spacing using wale size. When we return to the wale tie tab, we can see that for this example the spreadsheet confirms that bending does control at a maximum tie spacing of 36.57 inches based upon wale capacity only. Additionally, you can also see that the spreadsheet calculates a minimum tie capacity of 4,572 pounds, exceeding the selected safe working load of 4,500 pounds, using a 3x4 wale and a tie spacing of 36.57 inches. The user then selects a final wale size and tie spacing, in this case over here 3x4 wale with a tie spacing of 36 inches. The spreadsheet then applies these user input values to calculate the minimum washer contact area on the wales, right here, so that the wales will not fail in bearing, allowable compression perpendicular to the grain. And finally, the program checks the bearing stresses between the studs and wales and determines whether or not the allowable compression perpendicular to the grain of either the stud or the wale has been exceeded, which you can see in more detail by clicking on the Calculation Summary tab and scrolling down a bit on the page here. If we return to the wale tie tab, we can see that in this example, neither of the allowable bearing stresses were exceeded. So the spreadsheet returns a message that indicates that this stud wale configuration passes the bearing check. With the Braces tab, the user can input the various properties of the lateral bracing. The program assumes that no lacing or bracing will be used. For this example, the braces have been selected to be Douglas fir larch, number 2, rough 4x4s, assuming multiple use, and a moisture content of less than or equal to 19%. By inputting information in the brace spacing sheet down here, the geometry of the brace can be established. For this example, the top of the brace will be connected to the wall at 2 feet from the top of the wall, dimension D here, or 12 feet from the bottom. The bottom of the brace will be attached to the ground at 8 feet out from the base of the wall, dimension E here. The maximum length of the brace with the given geometry will thus be 14.42 feet. Additionally, given the cross-section of the brace, the spreadsheet determines that a maximum length of 15.10 feet based on slenderness ratio limitations, L divided by D, is less than or equal to 50. In this case, the user determines that the design length of the brace will be 15 feet right here. The design wind load is also established up here at 20 psf, applied at the top of the wall. Based upon brace properties input by the user, when we click on the calculation summary and scroll down to the area labeled brace axial load and slenderness right here, we can see that the program calculates the axial load capacity of these braces to be 2,486 pounds right here. When we return to the brace spacing worksheet, by clicking on the tab, we can see that the spreadsheet takes the allowable axial load of 2,486 pounds and divides it by the actual axial load of 294.5 pounds per foot. This calculation, that is 2,486 pounds, divided by 294.5 pounds per foot equals 8.44 feet, which yields the maximum spacing for the given brace with the given geometry under the given wind load. From here, the user would select a practical spacing based upon the length of the wall and modular dimensions, say 8 feet, center to center, to complete this formwork design example. Thank you for joining us in this short introductory video of the Easy Wall Form 2003 spreadsheet. You will find that the Easy Slab 2003 spreadsheet works in a similar manner to this one. We hope that you will recognize the benefit of using these spreadsheets to receive immediate feedback when solving a complicated design problem. It can be quite helpful to have a tool that can be used to verify your solutions when working on an engineering problem where the answer from one part of the problem directly affects subsequent steps in the design process. These spreadsheets can be very useful in developing accurate design solutions rather quickly and aid you in your educational quest for effectively learning how to design simple formwork systems.